3.9 Lesson 1, Exponential and Logarithmic Functions. Objectives. Today we're learning new differentiation rules. For the function f of x is equal to e to the x, we're learning today that the derivative of this function is also e to the x. This is a unique function in that its derivative is its own derivative. And then we have another function, g of x is equal to natural log of x, which is the inverse of the function e to the x. And today we're learning that the derivative of the natural log function is 1 over whatever the argument is. And that's over here. So we're learning those two differentiation rules. You will know the definition and properties of logarithms, especially the properties of logarithms, the logarithm of a power, the logarithm of a product, the logarithm of a quotient. They will help with finding derivatives of logarithmic functions. If you apply these properties of logarithms and expand your logarithmic function first, and then differentiate, it'll be easier to do. So you'll be able to find derivatives of exponential and logarithmic functions. That's the main objective for what we want to do today. To do this, we need to know these two differentiation rules. We can use the properties of logarithms to help us. And if you have a composition of functions, you will also have to use the chain rule. As we have stated before, all differentiation rules are ultimately proved using the definition of the derivative that we learned earlier. Now, there is a discussion for justifying why this differentiation rule is correct in your textbook, and you can take a look at that. And in that discussion, there is a reference. The discussion begins by using the definition of the derivative as a function. So it comes from the definition of the derivative that we've learned before. So now we'll go ahead and use that to find the derivatives of some problems, such as the first three examples that we want to look at. Find the derivative of each function. Number one, we have y is equal to e to the 5x. So you can see that we have the natural exponential function. So we will be using this differentiation rule to help us find the derivative for number one. But you need to recognize that you also have a composition of two functions for number one. So we will also have to use the chain rule. Here's number two. Our function is y is equal to e to the sine x. So we do have the natural exponential function, but we also have a composition of two functions, so we will have to use the chain rule here as well. Number three, we do see the natural exponential function. We have a composition of three functions, so we will have to use the chain rule here as well. So for number one, we want to find the derivative of this composition of two functions. So you should begin by understanding what the two functions are and the order in which they are composed. So we have e to the x and we have 5x. And in fact, which function goes to work first? Well, if you look at the input of x, it is being multiplied by 5, and then you're exponentiating with base e. So the function that goes to work first is multiplication by 5. That is the inside function. And e to the x is the outside function. So our inside function is 5x. And our outside function is e to the x, giving us e to the 5x when we compose them together. So now we will go ahead and find the derivative of this function using the chain rule, which you see here, and we will also have to use the differentiation rule that we're learning today. The derivative of e to the x is e to the x. So we have y is equal to e to the 5x. To find the derivative, we begin by thinking about the composition of functions that we have, And because we have a composition of functions, we must use the chain rule. So we begin by taking the derivative of the outside function, evaluated at the inside function. So that will give us the derivative of e to the x is itself, but we have to evaluate that at the inside function because we're using the chain rule. So we have e to the x evaluated at 5x, and then we have to multiply by the derivative of the inside function. So we have the derivative with respect to x of the inside function 5x, which is of course 5. So we have y prime is equal to 5 times e to the 5x. And we're done with number 1. So we have number 2 here, and we'd like to find the derivative of this function y is equal to e to the sine x. And what you have here is a composition of two functions. So just like we did in number 1, you should understand what the two functions are and the order in which they are composed. So you can begin by looking at the input x, and you can see that we begin by taking sine of the input, and then we exponentiate with base e. So your two functions are sine x and e to the x. The first function is sine because you begin by taking sine of the input, and then the second function is e to the x. You exponentiate with base e. So when this is the composition that you have, f of g of x, the first function is the inside function. The first function is sine x, so that is our inside function. And our outside function is e to the x. So we have e to the sine x. So our functions where f of x is the outside function, e to the x, and g of x is the inside function, sine x. And of course, the inside function is the first function, the outside function is the second function. So now, understanding that, we're ready to find the derivative using the differentiation rule for e to the x along with the chain rule. So to find the derivative of y is equal to e to the sine x, we begin by using the chain rule because we have a composition of two functions. So the chain rule says you need to take the derivative of the outside function, evaluate it at the inside function. Our outside function is e to the x. That's our outside function. So the derivative of the outside function is itself, but we have to evaluate that at the inside function of sine x. So that will be e to the sine x. And then we need to multiply by the derivative of the inside function. So we have the derivative with respect to x of sine x. And what is the derivative of sine x? The derivative of sine x is cosine x. So now you will have cosine x times e to the sine x. Here's our third problem. We'd like to find the derivative of the function y is equal to cosine of e to the 3x. You should begin by recognizing that here we have a composition of three functions. So we have to use the chain rule twice. And of course, one of our functions is e to the x, and that's why we're looking at it today. So when you look at the function y is equal to cosine of e to the 3x, begin by looking at the input. The first thing that we do to the input is multiply it by 3. So our first function is 3 times x. And then we exponentiate with base e. So our second function is e to the x. And then we take the cosine, so our third function, or our outside function, is cosine of x. And the order of these functions is 1, 2, and 3. So when you compose them together, you get y is equal to cosine of e to the 3x. So let me write the composition in the order in which they're composed. The first function is the inside function, which is 3x. So we have g of 3x. The function g is e to the x, so we have e to the 3x. And then we have the function f, which is cosine, so we have cosine. This now becomes the input for the cosine function, so we have cosine of e to the 3x, which is, of course, our function from number 3. But it's important for us to understand this so we can correctly apply the chain rule to find the derivative of number 3. So the chain rule states that we need to begin by finding the derivative of the outside function evaluated at the inside function and then multiply by the derivative of the inside function. So when we look at number 3, our outside function is cosine. So we begin by finding the derivative of cosine, which is negative sine. So we have negative sine of e to the 3x. And then you multiply by the derivative with respect to x of the inside function. The inside function for us would be e to the 3x. So you multiply by the derivative with respect to x of e to the 3x. Now e to the 3x is also a composition of two functions, so you would have to use the chain rule again. So we have negative sine of e to the 3x. Now the derivative here of e to the 3x, recognize that you have a composition of two functions where 3x is the inside function and e to the x is the outside function. So we have to use the chain rule again. The derivative of the outside function is itself evaluated at the inside function of 3x, and then we multiply by the derivative with respect to x of the inside function 3x, which is of course 3. So now we have y prime is equal to, this will give us 3. We have a negative 1 here, so we get negative 3. And I think I'll write this e to the 3x first. So we have negative 3 e to the 3x times sine of e to the 3x. And that's our final answer for number 3. So we just worked with the differentiation rule. The derivative with respect to x of e to the x is e to the x. And now we'd like to look at the other differentiation rule. The derivative of natural log of x is 1 over x. But before we do that, we'll look at the definition and some properties of logarithms. And then we will go on to the differentiation rule for the natural log of x. And then we will conclude by looking at a couple of examples applying this differentiation rule to find the derivatives of logarithmic functions. So we're taking a look at the definition and some properties of the logarithm. Definition. What does this mean? Log base b of c is equal to a. For example, you could have log base 2 of 8. What is that equal to? It's equal to 3. Why? Because when you take the base 2 and you raise it to the third power, you get 8. So for example, let's say you have log base 5 of 25, that would be equal to 2. Because when you take the base 5 and you raise it to the second power, you get 25. Let's take a look at another example. So here we have log base 3 of 1/3. That's equal to negative 1 because when you take the base 3 and you raise it to the negative 1 power, you get 3 to the negative 1, which is 1 over 3 to the first, and that is 1/3. So in general, if you have log base b of c is equal to a, that means when you take the base b and you raise it to the a power, you will get c. The base b has to be positive and not equal to 1. We say b, 5, 2, 3, those are called the base. You can see that this a here, 3, 2, -1, those are the exponents when we rewrite each logarithmic equation in exponential form. That is why we say a logarithm is an exponent. So this is a logarithm, and what is it? It's an exponent. It's the power to which you must raise 2 to get 8. This is a logarithm. What is it? It's an exponent. It's the power to which you must raise 5 to get 25. What is this? It's a logarithm. It's an exponent. This is the power to which you must raise 3 to get 1/3. Here are some properties of logarithms that will be useful for us when we do differentiation problems. The logarithm of a power. As you can see here, if you have log base b of c to the d power, you can take that exponent of d and bring it to the front and write d times log base b of c. You can also have the logarithm of a product. You have log base b of a product c times d. You can write that as log base b of c plus log base b of d. And then here you have the logarithm of a quotient. The logarithm of a quotient equals the logarithm of the numerator minus the logarithm of the denominator. So you have a quotient, log base b of c divided by d. You can write log base b of c minus log base b of d. The next differentiation rule that we want to look at is the derivative with respect to x of the natural log of x. It is equal to 1 over the argument. Now, using what we learned about the derivative with respect to x of e to the x is itself, we can use our differentiation rule that we learned before to show why this must be true. And here's how we can do that. We begin with the function whose derivative we want to find. Y is equal to natural log of x. So how can we show that the derivative of y is equal to natural log of x has to be 1 over x? We're going to use this definition of a logarithm to rewrite our logarithmic equation in exponential form. The base here is e. You have natural log, so the base here is e. So you have e raised to the y power is equal to x. This is just a different way of writing y is equal to natural log of x. We'd like to show that y prime, which is the derivative of natural log of x, has to be 1 over x. So how can we do that? You're going to take the derivative with respect to x of both sides of the equation. E to the y is equal to x. So when you do that on the right side, you get something pretty easy. The derivative with respect to x of the identity function x is 1. And on the left side, you have a composition of two functions where the inside function is y, and the outside function is e to the x. So to find the derivative of a composition of functions, you use the chain rule. So you find the derivative of the outside function. So you have e to the y because you have to evaluate the derivative of the outside function at the inside function. And then you multiply by the derivative with respect to x of the inside function y. And why do we do this? Because of the chain rule. But this is in fact what we're looking for. We're looking for the derivative of y with respect to x. That's what we're looking for. Another way you can write this is y prime. So you have y prime is equal to 1 over e to the y. But what is e to the y? Take a look at this particular step. E to the y is x. So we substitute x for e to the y, and we get our differentiation rule for the natural log function. So we're using the differentiation rule for e to the x to help us prove the differentiation rule for the natural log of x. And you can look at the discussion in your textbook for how we know this to be true. And in that discussion, we are relying on the definition of the derivative of a function. The definition of the derivative as a function. So ultimately, when we're working here, we are ultimately going back to the definition of the derivative as a function. So let's take a look at number 4 here. Find the derivative of each function. There are a couple of ways you can do number 4. One way is to see this as a composition of two functions where the inside function is 8x, and then use the chain rule along with the differentiation rule for the natural log function to find the derivative. If you do it that way, then here's what you'll do. You get y prime is equal to, take the derivative with respect to x of the outside function evaluated at the inside function. So how do you do that? The derivative of the natural log function is 1 over whatever the argument is. So you'll have 1 over 8x. And then you have to multiply by the derivative with respect to x of the inside function 8x. That's the chain rule. And then you get this derivative is equal to 8. So you get 1 over 8x times 8. And of course, this 8 will cancel with the 8 in the denominator, and you get y prime is equal to 1 over x. There's another way in which this problem could have been done, and if you do it this way, you avoid having to use the chain rule. You can rewrite the problem, you can rewrite the function using a property of logarithms. Here you have the logarithm of a product. The product is 8 times x. So you can write that as y is equal to the natural log of 8 plus the natural log of x. To find the derivative, you're going to recognize that natural log of 8 is just a constant. The derivative of any constant is 0, so you have 0 plus the derivative of natural log of x, which is, of course, 1 over x. And 0 plus 1 over x is 1 over x. So you get the same answer, but a different way of doing it. In the first way, we had to use the chain rule. In the second way, we began by rewriting our function using a property of logarithms, and we did not have to use the chain rule. So here we have our last example for today. Find the derivative. We have y is equal to natural log of x to the third power. There are two ways you can do this problem. One is to use the chain rule, recognizing that the inside function in this composition of two functions is x cubed, and the outside function is natural log. The other way is to begin by rewriting this function using a property of logarithms before differentiating. So let's go ahead and use the chain rule first. So when you want to find the derivative using the chain rule, you begin by taking the derivative of the outside function, which is natural log. And if you want to take the derivative of the natural log function, the derivative is 1 over whatever the argument is. So here the argument is x cubed, so you will have 1 over x cubed. But then you have to multiply by the derivative with respect to x of the inside function x cubed, because you're using the chain rule. So the derivative of the inside function is 3x squared. So you have 1 over x cubed times 3x squared. And you can cancel common factors of x that you have in the numerator and the denominator. So these two factors of x will cancel with two of these factors of x, and your final answer will be 3 over x. Now you can also get that answer without having to use the chain rule if you begin by rewriting your function using properties of logarithms, or in this case one property of logarithm, the power of a log, or the logarithm of a power. So if you use the logarithm of a power, you will have the power here is 3, and the logarithm of a power property allows you to bring this power to the front and write that as 3 times the natural log of x. So now to find the derivative, you would recognize that what you have here is a constant multiple, and when you have g of x is equal to k times f of x, where f of x is a differentiable function of x, then the derivative of the function g is simply the constant k times the derivative of the function f. So using that, you can just write the derivative of y is 3 times the derivative of natural log of x, which is, of course, 1 over x. So you have 3 times 1 over x, and when you do 3 times 1 over x, you get 3 over x. Same as what we had found earlier, where we used the chain rule, but here we're rewriting our function using the logarithm of a power property first before differentiating. So today we learned 2 new differentiation rules. We also reviewed the definition and properties of logarithms, and we looked at how to find derivatives of exponential and logarithmic functions.